Hi, class. So this is our second lecture in chapter 21. So this lecture will be on section 21.2. So if you haven't read it, you should go ahead and read it, at least after the lecture's over. We'll also be doing worksheet 7 on writing nuclear reaction equations. And that's what section 21.2 is about. It's about nuclear decay and writing nuclear chemical equations. So I have a short PowerPoint to go over as usual, and then we'll work on the worksheet after that. Oh, secondly, this backdrop that I have today, the periodic table, is particularly appropriate because you'll need a periodic table as you balance these nuclear equations that we're going to look at. So be sure to have a periodic table handy when you do the worksheet. And this worksheet needs to be turned in. So this is one of the two in this chapter that I want you to turn in. All right, so on to the PowerPoint. Okay, chapter 21.2, nuclear equations. So the first objective is to know the names of the symbols of the common nuclear particles. So these are the particles, the subatomic particles that are commonly found in nuclear reactions. Some of these are decay particles, so the radioactive decay occurs, and others are used to induce nuclear reactions. And so we'll go over those. You need to know the symbols, the names, and their masses and charges. Secondly, the second goal is to be able to write and balance a nuclear chemical reaction. So we'll get a lot of practice doing that using worksheet 7. And as I said before, you'll need a periodic table to do this work. So radiation, I just have a brief view of radiation here. It's energy that comes from in many different forms. It's the most common form of radiation is electromagnetic radiation. And that is distinct from nuclear radiation. Nuclear radiation originates from the nucleus of an atom, whereas the electromagnetic radiation can occur from electrical and magnetic events. There are machines that generate this. Sometimes they come from atoms, but there's a spectrum showing the range of electromagnetic radiation. On the very far side, where we have the shortest wavelength, the highest energy are gamma rays. So gamma rays in this image here, only gamma rays are nuclear radiation. They come from the nucleus. All the other radiations come from man-made sources or from atoms. If the radiation comes from an atom, it's from electrons changing their energy state from a higher energy to a lower energy. The gamma rays, it turns out, come from the energy levels within the nucleus. So it's the change in particles going from different energy level actually within the nucleus. So what is nuclear radiation? So we talked about this a little bit last time. It's the energy released by an unstable nucleus to make it more stable. And we actually calculated the amount of energy released in a couple of examples on the worksheet. The decay that occurs from one nucleus to another doesn't necessarily result in a stable nucleus initially. We'll see that later on in the next section. We're going to look at radioactive decay a little more detail. And sometimes it takes 9 steps before you get to a stable nucleus. So nuclear radiation comes in many forms. So we're going to look at many particles. Even though it's called nuclear radiation, most of what we're talking about is in the particle form. So the particles, subatomic particles with a tremendous amount of energy. The only radiation that actually is more like electromagnetic radiation, like X-rays, is gamma rays. So gamma rays do not have a particle component. So one thing about nuclear radiation, unlike the other radiation in the previous slide, is that it's always ionizing. So that means it breaks chemical bonds. It produces ions or free radicals. That makes it dangerous. But we've evolved in an environment of radiation. So we're surrounded by background radiation from the sun and the universe all the time. So our atmosphere protects us from most of that, but a lot of it gets through, especially the gamma rays. If we had a radioactivity detector right now sitting next to me, I would be picking up background radiation. So, you know, it's just something we live with, we've evolved with it. Our bodies have a way to repair the damage done. It only is particularly harmful if you're exposed to large quantities of it. So in this slide of your book, this shows the different common particles found in a nuclear event or a nuclear chemical change. And we'll go over these briefly. So at the top is an alpha particle. This is the heaviest particle. It's actually an helium nucleus. So it contains 2 protons and 2 neutrons. It's the heaviest of the particles because of that. It's doesn't have any electrons, so it has 2 plus charges. That's what these 2 pluses. So the alpha particle has a +2 charge. When we write the symbol, though, we don't include the charge. That's not necessary, but it's understood. It's a positively charged particle. A very light particle, we know that electrons are much lighter than protons and neutrons, is the beta particle. So that's about 1/20,000, 1/20,000, 1/2 to the 4th times less heavy than the alpha particle. So the beta particle is like an electron. So it has a negative charge. It comes out of the nucleus. We'll see another graphic the next time. This changes the nucleus. When a beta particle emerges from the nucleus actually changes. The subatomic particles in the nucleus change. The next one is a positron. That's the opposite of an electron. So the symbol is an E, but it's a +1 at the bottom. Sometimes they use a beta, a Greek beta for the symbol for a beta particle and for a positron. So again, this has a positive charge. It emerges from the nucleus, and it also changes the makeup of the nucleus when that happens. All of these do. They all change the makeup of the nucleus when they leave the nucleus, all except a gamma ray. Oops, let me go back up. Okay, next is a proton. Yeah, so we saw at the very first row here, we lost an alpha particle, which is like a helium nucleus. We can also lose a proton, which is like a hydrogen nucleus. So it's 1 proton. It's a positively charged particle. It's the weight would be the same weight as a proton. Another particle we can lose, we know the nucleus is made up of protons and neutrons, so it can also lose a neutron. A neutron has the symbol N, it has 0 charge and a +1 mass. And the last gamma ray, and the gamma ray isn't really a particle, it's just it's a light, it's electromagnetic radiation at very high intensity, much more energetic than X-rays. So that's the most energetic energy that we know of, at least that we're going to talk about. And that's it. Here's another graph that shows these same particles. So a couple of things about these symbols. You notice on these symbols, there's two numbers, and these are the same kind of numbers we see when we write the formula for an isotope. So it's the bottom number is the number of protons. It's almost like a charge. It's a charge. Oops, let me go back up again. Sorry about that. So it's like the charge. Remember, the number of protons is equal to the charge in the nucleus. So this is a charge. So the 2 here for helium means a +2. The -1 for electrons mean it's a -1 charge. And we'll use these like atomic numbers also. So when we balance the equation, we'll add or subtract these together depending, and I'll go over that. The number at the top is the mass number. So that's how much the particle weighs in nucleons. Remember, the protons plus neutrons are called nucleons. So the particles that live in the nucleus. So that's the number of nucleons. And what happens, so the symbol for helium is He24, or for the alpha particle, or just an alpha. So the alpha would look like this. I wonder if I can draw an alpha. Maybe I can. I tried this once before. Alpha. I'm going to draw an alpha up here. Here's an alpha. Looks like this. Okay, so that's what we use for a alpha particle also. We use that symbol. That was on the previous slide. So what happens? Here's a nucleus, schematic of a nucleus with protons in green and neutrons in white. So we lose an alpha particle, we lose 2 neutrons in white and 2 protons. So when that happens, the new nucleus has 2 fewer protons and 2 fewer neutrons. So A decreases by 4, because remember, A is the number of neutrons plus protons. So that goes by 4, and Z goes down by 2. When you lose an electron, a beta particle, well, the beta particle changes the number of neutrons. Now you can think of a neutron. Remember, a beta particle is negative, or an electron is negatively charged. A proton is positively charged. If they combine, you get a neutral particle, which is like a neutron. And so when we lose an electron or a beta particle out of the nucleus, one of the neutrons, circled in red here, becomes a proton. So if you think of, I'll use my annotation here again. This is something new for me. So you think of a neutron as a positive and a negative. When you lose the negative, what's left is a positive. So that's a good way to think about it. So that means the Z goes up by 1. In the gamma decay, that doesn't change the nucleus. So the A and the Z stay unchanged. In a positron emission, the symbol for positron, remember, was an E with a +1. So what happens if this is a plus and a minus? So if we have a positron emission, oops, when we lose a positron, a positive, that's like losing a, like losing a proton and changing the proton into a neutron. So the Z decreases by 1. The A remains unchanged. So the total mass doesn't change, but it's the opposite of what happens to an electron. So when we lose a beta particle, you end up with a positron. When you lose a positron, you end up with a new neutron. It's the opposite. And what you can think of is, let's see, I don't know if you can think. I guess what happens, if this is a plus and a minus and you add a plus to it, you get another neutral. Well, that doesn't work with positrons so well. Electron capture. So electron capture is a case where you take an electron from one of the valence, not a valence shell, but one of the inner shells of the atom, maybe n equals 1, and the nucleus will capture an electron from the one of the shells, one of the its own outer electron, and it gets trapped by the nucleus, and so the positive combines with the negative and makes a new neutron. So the number of protons goes down by 1, but the mass remains unchanged. So electron capture and loss of a positron, or positron emission, is leads to a similar change in the nucleus. So let's just a minute. I want to add something. Remember the stability of the nucleus had to do with the ratio of the number of protons, excuse me, the ratio of neutrons to protons. And we saw a graph of that in the previous lecture. And so if you produce more neutrons, which means the Z decreases by 1. So in these two cases, in the last two cases with positron emission and electron capture, the Z, which is the number of protons, goes down. So that means that ratio N over P goes up. So that would occur, if you remember our blue line of stability, so the radioactive elements that are below that blue line have too many protons. That ratio N over P is too small. So if you do a positron emission or an electron capture, the N over P increases and the nucleus gets closer to that line on that graph that showed the stable nucleuses, stable elements. On the other hand, if the N over P is too large, that means what we have to do is we have to increase the protons. So which one of these processes increases protons? It's beta decay. So Z increases by 1. So if we're looking at that ratio N over P, and let me write that again so you can remember that. Let me put that right over here. So N over P in a beta decay, we're going to increase that. So this increases. So N over P increases in beta decay. So those would be the elements above the line. They're unstable above the line of stability, and they have too high a ratio. So we're going to increase P. Oops, I did that wrong. I did my error wrong. So let's go back. Let's go like this, and I'll erase that. We have an eraser. See an eraser, so I'm just gonna black that out. Okay, this would be the feather. So yeah, so if P increases, that ratio is gonna go down, right? I think so. So in these two processes, where we decrease Z, N over P is going to increase. So N over P is going to increase. All right. So on to the next slide. Let's see what's the matter. Come on, there we go. Well, look at all that stuff I've written all over. It's still up there. So Let's look at nuclear reactions and nuclear equations. So the general form of a nuclear decay equation is you have a radioactive nucleus undergoing decay. So you have a radioactive nucleus and then a reaction arrow. It goes to a new nucleus plus the radiation emitted. So if you have a sentence, if you're reading a sentence that describes a nuclear event and it says that radiation is emitted or radiation is formed, that's a decay event. And so a typical, a common radioactive decay that occurs in nature is the decay of uranium-238, and that decays with the emission or the loss of an alpha particle to produce a thorium-234. So is this balanced? So the way you determine if a nuclear decay equation is balanced is you add up the Z numbers, which are on the bottom. So the Z on the reactant side, the total Z on the reactant side, which is 92 in this case, has to equal the total Z on the product side, which is also 92. The A number, which is the mass number on the reactant side, 238, has to equal the mass number on the product side. So that's pretty much. So in this case, the mass number is 238. So the total mass on the product side must also equal 238. And it does. So this is a balanced nuclear equation. Atomic number, or the Z number, also has to add up. Reactant has to equal product. So here is the alpha particle is a product of this alpha decay. So what is the radionuclide, or what is the product? One way we describe this is in a radioactive decay, the reactant is called the parent radionuclide, the parent radionuclide, and the product is the daughter radionuclide. So in this case, we're asking what is the daughter radionuclide from this decay reaction? So because recognize the alpha particle, because the mass numbers have to add up, we have to do a little bit of algebra that says 224 equals x plus 4. So x is going to equal 224 minus 4. It's pretty simple math to balance these. So the number is going to be 220. I think you all knew that before I finished talking. On the Z number, the 88 equals x. We put x here plus 2. So x is going to be 86. So now here's where you need to use your periodic table. You have to look up element 86 unless you've got it memorized. So if we look up element 86, it turns out that it's radon. So you put in the symbol there, 86 radon 220. So it's radon 220. So that's how you balance the equation. And if you have everything except one particle, you can balance either side of this equation. So if we had radon and the alpha particle, we'd know it came from radium 88. So if we didn't know this, you could figure it out if you have those two. If you have the products, you can figure out the reactant. If you have the reactant and the decay particle, you can figure out the daughter nuclide, radionuclide. Here are a couple of other examples. Here's an example of beta decay. So in beta decay, if you look at the parent radionuclide is manganese 56, and with an atomic number of 5, the beta particle is a -1. So that means we're looking for element 26. If you look that up, that's iron. So we would put 26 here, write in the iron symbol, and then make sure that the mass number doesn't change, because the mass number of an electron is 0. So our daughter nuclide here is iron 56. Here's an example of positron emission. So in the case of positron emission, it has a +1 Z number. So that means that the element, remember we said when positron emission occurs, we lose a proton. A proton changes to a neutron, so the mass number doesn't change. So we lose a proton, so we go from manganese 25 to a chromium atom, and that's chromium 56. So manganese 56 turns into chromium 56 with the emission of a positron. The positron, by the way, is the antimatter particle of an electron. If they collide, what you end up with is two gamma particles. They just annihilate each other and turn their masses. They don't have much mass anyway, but it turns into pure energy in the form of gamma particles. I think that's described in your chapter. So producing, here's some other kinds of nuclear reactions. This isn't a radioactive decay reaction. This is a reaction where you, it's a subatomic particle capture. So this is where oftentimes you can bombard an element with neutrons, and that element will change into another element. So in this case, we've bombarded molybdenum 98 with a neutron. Now it didn't change into a different element yet, but it turned into molybdenum 99. So you can see that if we didn't know what this element was, you could just add up the Z numbers and the A numbers to get the formula for the product here. And then molybdenum 99 then is radioactive and with beta emission, and turns it into technetium 98. The M there means it's metastable. That means it's kind of a weird nucleus in between 98 and 99. And these metastable nuclei always are give off. They don't last very long. So I'm not sure if it even has a half-life. We can look it up, technetium 99M. But it turns out that that particular metastable nucleus, technetium 99M, turns into technetium 99 with the emission of a gamma. So it turns out that this is a useful element in medical diagnostics. So they use technetium, metastable technetium 99 in medical diagnostics, and they detect this gamma ray. Okay, so that's it. For the lecture, let's look at the worksheet now and balance a few of these reactions. So I'm going to go straight to the worksheet. I'm going to go open up this other slide. I think if I go speaker view and I click on it, it'll appear. Let's see. There it is. Okay. So I'm going to have to learn how to erase my screen. Those symbols are still up there. So let's look at this worksheet. So look at the table of particles commonly found in nuclear reactions and answer the following questions. What decay particle is actually a nuclei? So I'm going to let you finish these, answer these, and turn these in with your worksheet. I will post, as usual, after probably later next week, I'll post the answer key for these. And you can check your answers. I will be checking your submissions, so I will reply to each of your worksheets that you turn in. So let's work on the next one though. Let's work on number 2. Balance the following nuclear reactions by filling in the boxes. Use the correct symbol for each particle you identify. Okay, so this is an exercise in just balancing the atomic numbers and the mass numbers. So in the first case, we have thorium 234 losing an alpha particle. So what's it going to turn into? Well, the way I like to do this, I usually like to find the element first. So we have the alpha particle loses 2 protons. So that means we have 90 minus 2. So this is going to be 88 here. And I have my handy dandy periodic table right next to me there. And if I look up my periodic table, 88 is radium. And the mass number then is 234 minus 4, so that'd be 230. So I have radium 230. Then we can check 230 plus 4 is 234, 88 plus 2 is 90. So that's the right answer for that one. Let's look at the next one. And I'll let you do the last one. The next one has element 1 and element 2. Well, we know element 1 is hydrogen. And element 2 is helium. So you just plug those in. So the Z and the A are already given. So we just put in the symbols there. We're producing a helium atom. This isn't a decay reaction. This is, the first one was decay. This is decay. This is some other kind of nuclear reaction. And later on, we're going to learn that this second reaction, B, is called a fusion reaction because we're fusing 2 smaller nuclei together to make a bigger nuclei or some new nucleus, new atoms. And so we can figure out what goes into these boxes by looking at the reactant. So the Z number on the reactant is 1 plus 2. We have 2 here, so this has to be 1 here. And then the top is 2 plus 3 is 5, 4. So this has to be 1. So we know that element 1 is hydrogen. So that's the answer for that one. I'll let you guys do this one. So you do this one on your own. Let's look at the next one. So this next one is where we have a plutonium atom. It's my little handy dandy periodic table that I was using. You have a plutonium atom being bombarded with high energy neutrons. When that happens, the plutonium atom splits. Whoa, it splits into ruthenium and tin. This is called fission. This is a fission reaction, fission. This one I call fusion. So we have decay, fusion, and fission examples in this worksheet. It's pretty cool. Come on, focus, there it goes. And so what we want to know is how many neutrons are produced in this fission reaction. So we're going to add up the Z numbers. So we have 44 and 50 and 0. 44, 50, and 0 is 94. Okay, that's good. 129 plus 109. Looks to me like that's 238. So we have 238 here. And over here we have 240. So we're missing 2 nucleons or 2 mass numbers on this side. So I think we need a 2 here. If we put a 2 there, that's 2 times 1 is 2, plus 129 makes it 131, and 131 and 109 is 240, which is what we get on this side. 238 plus 2 equals 240. Okay, so that's how we solve that one. Number 3 says, what type of radio decay process has occurred in this following equation? So this question is just identify that. Tell me what decay that is. Up here, this was alpha decay. Alpha, so the very first problem up here at the top, we had an alpha decay, right here. So I'll let you answer that one. You figure that one out. Number 4, it says U-238 decays into thorium-234 and an alpha particle. Write down the full decay equation. So I'll let you do that too. I'll let you practice writing. So you guys do this one too. You write that one. You can do that. And then in number 4B, calculate how much energy is released. So this is a practice from what we did previously. This is a pretty easy one. So I'm going to, I'll do it now. So I'm going to add up U-238 decays into thorium and alpha. So that means, remember that the mass, we're looking for the mass defect or the mass difference between the reactant and the product. So U-238 says over in the right weighs 238.0, whoops, that one, 0508 minus the thorium-90, which weighs 234.0426 minus the alpha particle, which is 4.0026. And if we do all that, we get our answer. I had all this worked out once before, but I'm going to have to do it again. 238.0508 minus 234.0426 minus 4.0026 equals 0.0056, and these are all AMUs. So let me put U in front of all these. These are all AMUs. So you have 0056 mu, and this is our mass defect. I think that's what we call our mass defect. And so if we look at, we want to convert our mass defect into, we'll use million electron volts. That's pretty easy. So we have 0.0056 times, we want our conversion factor of capital M E V over AMUs. And we can look that up. Excuse me for a minute. All right, I'm back now. I'm looking at my cheat sheet that we used last time, and it says there's 931.5, 931.5 MeVs per 1 AMU. So we're going to multiply those together. And I still have 5.6 times 10 to the minus 3 in my calculator. So that'll make it easy. 931.5 times 0.0056 AMUs, and I get 5.2 million electron volts for that nuclear reaction. So that's it. So the next lecture will be on section 12.3. If you have any questions, as usual, send me an email or a text or join me in office hours. So take care. See you next time.